All right. So today I would like to continue on from the discussion of address translation and look at chapter 16 of the Operating Systems 3 Easy Pieces book, where we look at segmentation. We look at segmentation. And last time I made like a little scrappy simulation for address translation, virtual memory, a virtual address translation, using the base bounds method, where basically you have two registers on the CPU, where you have a base register and a bounds register, and the base register is responsible for telling you where where an address space is located in physical memory, where the start of an address space is located in physical memory. And the bounds register tells you how big the address space is. And with those two registers, we saw that there was a way where you could translate any virtual memory address associated with that address space. You could translate that into the corresponding physical address. Physical address. And you could also error check as well, making sure you weren't accessing an illegal address. So we did something like that, and that was pretty cool. But one of the major issues with that method is with just a single base bounds register pair, you have to kind of keep the address space contiguous in the physical memory as well. So the abstraction pretends that the address space is contiguous, but by this particular method, you also have to make this block, you have to place this block contiguously in physical memory as well. And what is the problem with that? Well, if an address space, oh wait, this is the virtual address space, sorry. The virtual address space looks like this, right? You have the code segment, or the code section, the heap section, and the stack section on the bottom. And between the heap and the stack, there's this free memory, which has been allocated to this particular address space, but isn't being used yet. But we can see in the physical memory, using the space bounds method, we can see that this address space has been translated into the 32 kilobyte address, right? So we pretend it's from 0 to 16, but it's actually from 32 to 48. And we can see that, this code segment corresponds to that code segment, heap, stack, and that free space is allocated here. Now, what you can imagine is this free space is kind of wasteful because it's being allocated with this address space for this particular process, but it's not being used. And it will be used in the future as the process or the program, makes more variables and allocates more memory or whatever, but maybe it won't use that memory and it's a waste. So we call this idea, this wasted memory, we call it internal fragmentation because it's a fragment of memory that is within or internal to the address space and it's being wasted. So that's a problem with this sort of method. So chapter 16 talks about segmentation. And it's not a terribly complicated thing if you understand chapter 15, but chapter 16 basically says instead of giving one base bound register pair for the address space, what if we give a register pair, a base bound register pair, to each individual segment in the address space? So essentially, you can see in this particular table, if I have a code segment, a heap segment, and a stack segment in the address space, then the code segment gets a base bounds register pair. So in this example, the code segment was placed at 32 kilobytes, and the size of it is 2 kilobytes. Heap is placed at 34 and is of size 3, so 34 to 37. Stack is placed at size 28 and has a size of 2. Stack is interesting because it grows upwards instead of downwards. The base register talks about the bigger address number as opposed to the smaller one. For the other two, code and heap, well, code doesn't really grow, but heap, because it grows downwards, we look at the smaller address number, 34. But, we'll talk about that more a bit. But the thing to realize now is by doing it like this, where each individual segment gets a base bound register pair, we can kind of place them independently in the physical memory. we pretend the abstraction, the address space abstraction says that, we have the code at the top, then the heap, and then the stack. But in reality, in the actual physical memory, you can have, the stack here first, and then the code, and then the heap, for example, just as an example. So by doing it like that, the memory between that sort of free memory in here might not actually be present or allocated in the physical memory, because we are able to place these individual segments independently. So yeah, that's the big idea there. So then there's some examples on what to do exactly. I think the middle example is probably the good one. Imagine I want to translate address 4200, which is located sort of, maybe I'll get my pen, which is located just inside the heap, right? It's like here. That's a big marker. I meant to take the other pen. That's fine. So yeah, 4000, was it 100 I say? 4200 is like located there. So it's somewhere in the heap, a little bit past the heap. In the old version, chapter 15, we would find this offset, which would be 4200, right? Because from 0 to 4200 is 4200. We would find that offset. We would then find the address space in the physical memory using the base register. Maybe I'll take the previous. We would then find the address space in the physical memory, which would look like this. And then we would go 4200 down from that top and find the spot. I've lost it. Why is it? Okay. We go 4200 down until we found the spot. And that would be how we found the physical memory address. However, now that we have these three sort of independent segments in the physical memory, we can now look at the heap specifically and say, well, the heap is located at 34 over here. So instead of looking at this overall offset, we can instead look at just this little offset in here. So how do we figure that out? Well, we know that this address is 4200 in the overall virtual address space. So the offset between here and here is actually 104. Something to remember, 1 kibibyte is 1024 bytes. It's just one thing to remember. So finding this offset of 4200 minus 4 kibibytes gives you 104 bytes. So instead of going from the top and going down like this, we can go from here and go 104 bytes down until we hit that spot. So we would do 34 kibibytes plus 104 bytes, and we would get this, and then we would get this as the physical memory address, the translated physical memory address. So that's the idea. We have this extra idea of an offset for a particular segment. In chapter 15, the offset was always found by going from 0 up to the virtual memory address. So it was always equal to the virtual memory address. The offset was always equal to the virtual memory address. But now, because a segment doesn't necessarily start from 0 kibibytes, the virtual segment doesn't necessarily start from 0, right? Because the code segment might start from 0, but all the others might not. We now have this extra step of looking for the particular offset. Anyway, so that's the basic idea. Of course, there's still this idea of like, we have to do some error checking in case we look for like 8 kibibytes, the address 8 kibibytes, which would be like over here, which doesn't correspond to any of the particular segments, right? That'd be a problem. Or if we went like 17 kibibytes, that would also be a problem. That's like way outside the address space. -1 kibibytes would be a problem, right? It's outside the address space on that side. So there's some error checking to do there, but generally we're okay. There's some general formulas we can use, but I think I'll do that later. Now, I said when we did this example, I said that, by looking at the diagram, we know that we're in the heap, right? By looking at the diagram, looking at address 4200, we know we're in the heap. But the computer can't look at the diagram, so to speak, right? The computer has to sort of be a little bit more precise, or needs a different approach to figure out what segment it's in when we're looking at a particular virtual memory address. So, how does the computer know what segment a virtual address is in? Question mark. And so there's two approaches that the book talks about. The explicit approach is what I'm going to be doing today because I think it's a bit easier, but it does have its limitations. The implicit approach, I think, is what real operating systems do in modern times. but it is more complicated, so I won't be doing it. So basically, we chop an address space. We chop the, not the address space, rather the a memory addresses. We chop the memory addresses into segments, different segments, not the same as memory segments. Maybe portions is better. Different portions based on the top few bits. Okay, so basically, just to note from this example over here, sorry, it's a 16 kilobyte address space, which means it's 16 times 1024. There's 16,384 addresses, right? Which means it's a 14-bit address space. Because if you look at 14 bits, basically, based on the binary, you have two options for each spot, right? So you have 2 to the 14 kind of addresses you can make, which is the same number, right? So having 16 kilobytes means you have 14 bits available for your address space. Like any memory address you make can be made with 14 bits, is what I'm trying to say. So if any address can be made with 14 bits, what this explicit approach is saying is take a few of the top bits and use that as kind of an indicator as to what segment you're in. So what do I mean specifically? The code segment, any address in the code segment must always start with 2 0 bits. So what I've highlighted in yellow. The first 2 bits of the code segment address must be 0 0. The first 2 bits of a heap address should be 0 1, and the first 2 bits of the stack segment of a stack address, should be 1 1. Now this is sort of these specifics is just for the example. Of course, in reality, we have like a 32-bit address space or like a 64-bit address space on modern machines, right? So 14 bits is quite small, right? The idea of having 16 kilobytes for an address space is quite small. Having said that, it is a good example. Now, what is the major limitation of doing? Oh, well, maybe I'll first say this, yeah. So the code segment in the virtual memory starts at 0. We kind of knew that already, but this is really confirming it because the first 2 bits is 0 0. So, the very first address you can have in code is 0 0 0 0 0 0, etc., right? As I've written in here. Now, the very first address you can have on this heap is 0 1 0 0 0 0 0 0, etc., right? So this heap segment starts at 2 to 12, right? Because it's this number in here, 0 1 0 0 0 0, is equal to 2 to the 12 when you convert binary into base 10, which is equivalent to 4 kilobytes. You can check that by using the 1 kilobyte equals 1024 bytes. And then, stack is a little bit different again because it grows upwards, but the way I've written this is I've said 1 1 1 1 1 1 1, etc. is the biggest address the stack can make, and we'll talk about how the stack starts at the bigger address and grows upwards, grows towards smaller addresses. So, a stack address always starts with 1 1, and the biggest address is going to be 2 to the 14 minus 1. This 1 1 1 1 1 number is equivalent to 2 to the 14 minus 1 when you convert binary into base 10, which is equivalent to 16 KB minus 1. If you do 2 to the 14 minus 1, it will be the same as 16 times 1024 minus 1. Right? So that's a sort of extra, that minus 1 is a little detail to think about. When we say, when I say 16 KB over here, that means that this spot here is 16 KB. The stack actually finishes 1 byte before this spot. So, this actual address space actually goes from 0 to 16 KB minus 1, which is what I've written here. The address space goes from 0 to 16 KB minus 1 byte. So this 16 KB I've written down here is actually just past the stack segment. So that's something to bear in mind. But anyway, you can see this range gives us a total of 16 KB addresses to work with. Anyway, now the major limitation, this is what I'm going to talk about. The major limitation of doing this is because the code segment is fixed to have 0 0 at the start, you only have 12 bits left that you can actually work with. You can actually modify to make different addresses in the code segment, right? Because the first 2 are always fixed, so there are only 12 left to play around with, which means you actually only have 2 to the 12 addresses you can make with the code segment, which is equivalent to 4 kilobytes. Is that right? Yes. 2 to the 12 is equivalent to 4 kibibytes. So with 12 bits in the offset section, like if this is the, I forget what this is called, segment section, I think. This is called the offset section. We'll see why in a second. But with 12 bits in the offset section, each segment has a maximum size of 2 to the 12 equals 4 kibibytes. You can only make 4 kibibytes worth of addresses when you only have 12 bits to work with, because again, the first two are fixed. So that's a major limitation of the explicit approach, is you're always going to be limited in the maximum size of your segment because you only have so many bits to work with. The implicit approach is interesting. Basically, the book is a bit more brief about this. It just says that the hardware essentially determines which segment a particular address belongs to, a virtual address belongs to, by looking at how the address was formed. Like what kind of instruction was being used to work with this address. You know, was it some kind of memory allocation indicating it's relevant to the heap? Is it some kind of instruction fetch kind of thing, code fetch instruction, which means the address is probably relevant to the code segment? Is it sort of a stack pointer thing or whatever, blah, blah. So, you know, there is this implicit approach that I think I might be able to look into later on, but for now, this is kind of just interesting reading and not too much of a problem. Now, focusing on the stack is a little bit weird because it involves something that grows upwards or towards smaller addresses, right? The heap grows down from small addresses to big addresses in a downward direction. Stack grows up from bigger addresses to smaller addresses. I believe that's just convention. I'm sure you could swap things around and see what would happen, but we're going to be following convention. So we need to consider the stack differently because it grows in the opposite direction to the heap. So what we generally do is we make the base register point to the bottom address of the stack. So, we make it point to 16. We make the base register point to 28 kibibytes. Now again, 28 kibibytes is actually the address just below where the stack starts. So the stack actually starts at 28 minus 1, 28 kibibytes minus 1 byte, but 28 refers to like just that point right after the stack. Where am I? I've lost everything. Oh yeah. So that's because the reason we point to the bottom of the stack, the bottom address, is because that's where the stack starts. In general, we need to keep track of whether a segment grows towards the larger address or towards the smaller. Yeah. So in general, we keep track of in what direction a segment grows. And so this extra bit of information is required. We talk about, in what direction do you grow? As an example, if we want to translate the virtual address 15.5 kibibytes, that would be over here. That would be over here. So 15 is here, so 15.5 would be like here. What we end up doing using these numbers of 28 kibibytes and 2 kibibytes, and bearing in mind that we know that the stack is a maximum of 4 kibibytes, so this is 2, but the stack can be a maximum of 4 kibibytes by the explicit approach, we can do something along the lines of saying, well, I know 15.5 is 0.5 away from the bottom. So then instead of going from the top, we actually go from the bottom, which means we have to subtract 28 kibibytes minus 0.5 kibibytes and get 27.5 kibibytes. So the offset, this is the difference. Because it's going upwards, we're actually subtracting the offset, not adding the offset. Before we were adding the offset, right? We said 4 kibibytes plus a little bit, I forget exactly, 104 or whatever. But this time we're saying minus 0.5 kibibytes. Yeah, so that's the major difference. That's why we have to be careful about knowing in what direction a segment is growing in, because it will make a difference. Okay, so that's fun. OS support. Oh yeah, and then there's just like normal stuff, like what the OS has to do to make this work. There's this thing called external fragmentation, which is annoying. Which I'll talk about in a second. First things first, you have to think about what to do in a context switch, which is just about basically saving the state of the old process and bringing the state of the new process, restoring the state of the new process. Remember that a context switch is basically what happens when an old process it gets paused and a new process resumes. That's all that is. So, there's considerations there. How does the OS allow a segment to grow? basically sometimes a stack has to grow or the heap has to grow, right? If you need more space. Sometimes that's relatively straightforward if the segment already has some free space to work with, some unused space. But sometimes the OS itself has to actually make the segment take more space in physical memory. I don't think I'll focus on this too hard because I think this is kind of I don't know. I probably won't do this, but it's fine. Managing free space, I'll probably need to do. When you need a new address space, when a new process comes onto the system, when a new address space is required. So the OS has to look for memory, physical memory, to place that address space. This is a bit awkward now because segments can be different sizes. So like you might expect before when we had all address spaces be the same size, it was just about putting address spaces in very fixed blocks over and over again. But because we're now splitting these segments into different sizes, right? The code segment and blah blah blah, they might be different sizes, so it's not as easy to make assumptions about what's happening. It's easy for the physical memory to get little holes between segments because you're like putting segments of different sizes and you're just putting them where they can fit, which might mean that there are these little holes in memory. And we call this external fragmentation. So before we had internal fragmentation, now we have external fragmentation. So things like this can happen. So like the things in black are the used memory, and then the things in red are like the little holes of free space that are existing. And in this particular instance, what might happen is if someone requests for 3 KB, you have 3 KB available, but because they're not contiguous, it's possible for this request to be rejected, which would be a shame, right? Because it's like you have 3 KB available, it shouldn't be rejected, but because they're so separate, the 3 KB segment might not be placed correctly. So solutions for external fragmentation, the one that I will be doing is I will be compacting the physical memory. So basically, we're going to move the allocated spots, the black shaded spots, to make a contiguous region. So like from this thing, we'll move it so that it looks like this. These 3 rectangles will be moved up to make one big rectangle, and then the red ones will be moved down to make. So this free stuff is now contiguous. So that 3 KB example will now be possible. Now the natural limitation is copying memory like this is very inefficient. Like we have this idea of every time you want to move a segment like this guy up top, you have to change its base and bounds, of course. The base now has to go over here. The bound maybe actually can stay the same because it's the same size. But the base has to be updated. But the other thing is all this memory, the data in here has to actually be physically, transferred over, copied across to over here now. So that's going to be annoying. And if it was for one segment, then maybe that's not a huge deal. But you're doing it for every single segment, basically. So that's going to be a problem. You can also use a free list management algorithm, which I could look into more, but apparently it will be talked about in a later chapter, so I didn't explore that too much. So that's basically the main thing. Yeah, that's basically the overarching ideas. So I've kind of been thinking about this for like a little bit, and I've been thinking about the kind of different structures and things I need. So the things I'll need, I'll need like something to represent physical memory. So like an array of physical memory that's like 64 KB in size. And maybe the physical memory struct will have a pointer or an integer telling me how much free space is left. So I can easily determine if I have sufficient space for a new segment if needed. I'll have a struct called segment, which has a base and a bounds value associated with it. Something that tells me if it grows up or down, and something that tells me its protection. So that's just translated from this table. The segment struct is basically to give me that. PCB, the process control block, will tell me information about the process. In this case, I think what I need to know is what are the segments that are associated with that process. So the code segment, the heap segment, and the stack segment. What are the segments associated with the process? I think that's all I really need for a process. And I'll have a process table as well, a process control block table, so to store all the processes. I need an MMU. So the MMU is the memory management unit. That's the hardware basically responsible for keeping the stuff working. So it needs a segment register. It needs a what? Oh yeah, it needs 3 pairs of basebound registers is what this is. Um, yeah, it won't actually be a segment though. It'll just be a base register and a bound register and a base. It'll be 6 basebound. It'll be 3 base registers and 3 bound registers basically. Um, where each pair is for either the code segment or the heap segment or the stack segment. So that should be fine. Yeah. And then like I was thinking about the different kind of functions I would need. Probably I need a translating function, of course, to translate between virtual addresses and physical ones. Segment placing function to be able to place a new segment. Address placing function, which I think will be like a more abstract version of the segment placing function. In my head, like the address placing function will call this function 3 times to place the segment, to place the code segment and the heap segment and the stack segment, and then a compacting function to help with like when this happens. And yeah, and then I was thinking about how am I supposed to place a segment. This is probably the part that's going to be the most dumb because I haven't really looked into how free. I think the next chapter is about free memory management, but I haven't read that yet, so I don't know what's going on. So I'm just going to do something really simple. I'm going to have a linked list of nodes that tell me sort of the contiguous blocks of memory where there is free space, and then every time I use a bit of that, let's say, let me draw this out. Oh yeah, so we'll start like this. From 16 kilobytes to 64 kilobytes, there is this free space. Note that 0 to 16 is taken by the operating system. I think there should be a drawing somewhere. Like here, yeah. So from 0 to 16 in the book, as an example, rough example, is taken by the operating system. So, and that's why it doesn't go from 0 to 64, it goes from 16 to 64 because 0 to 16 is taken by the OS. So the free space starts with 16 64. Let's say a segment comes along that uses 16 to 32. It will basically look at this node and replace it with 32 to 64. And then let's say another segment comes along and it uses 42 to 48 gets used. Then this was a node that points to null. This node will get split from 32 to 42 and from 48 to 64. So now I have 2 nodes of free space, but each of them are a bit smaller because I use some from the middle. Yeah, and then I have this idea of like for upgrowing segments, look from downgrowing segments, look from left to right. So look at the smaller addresses first and try to find a suitable segment, a suitable bit of space that I can put the segment in. And then for upgrowing segments, look from right to left. So go from the right side and go this way. So I'll need a doubly linked list actually. That's fun. All right, anyway, so that's the basic thing. That's what I'm gonna try, and we'll see if we can do. And then I have to think about like how to actually give input. I'll probably do something similar with the files like last time, but yeah. So I've done a bit. I've written a little bit of like basically just taking all this stuff and just throwing it into code. There's a little bit to talk about, nothing major. Basically, we're assuming a 14-bit address space because that's what we've been doing in the examples. But because there's no 14-bit integer thing, we'll be using 16-bit integers for addresses, and we'll be using the left 4 bits for the segment section and the right 12 bits for the offset, right? So like how we're talking about over here, that's wrong. How we're talking about over here, we had 2 bits in the segment section and 12 bits in the offset. Because we're using 16 bits now, we'll use 4 bits in the segment section. That's fine. So yeah, 16 bit space size, the max address. Oh yeah, so a few constants. I said the max address is the unsigned integer, the unsigned integer is 16 max. So basically imagine 16 bits, all of them are ones. That's what this value is. Do I have to say numseg bits is 4? Yeah, because of that. That's what this is. Seg mask. Okay, so seg mask refers to, in this case, a seg mask refers to 4 bits in the significant. So the left 4 bits are going to be ones and the rest are going to be zeros, because that way I can AND any address with the seg mask and I can figure out what the most significant 4 bits are. So what am I doing? I'm taking the max address, which is all ones. I'm shifting it down by the number of seg bits, which will make basically 4 zeros followed by a bunch of ones, and then I'm knotting it to flip that around. So it'll be 4 ones and then a bunch of zeros, which is what I want. This is the same thing as unsigned integer 16. And then the offset mask is basically 4 zeros followed by 12 ones. So I do the same thing, and I XOR it with the seg mask, and that will flip basically everything. Wait, could I just say not max address? Do I need to XOR it? Am I dumb? Hang on. If I just say, because what did I say? The seg mask is 1111 00000 12 times. So if I not it, it will be 0000, and then, yeah, okay, I'm dumb. I can just do that. Fantastic. And then, yeah, so then I have some types. I have mem address to be like, if I ever want to handle addresses, they should be of type mem address, which is just an unsigned integer 16 of 16 bits. Mem size is the size of the, how many bits. Why do I have that? Actually, I don't know why I did that, but maybe I'll use it. Oh, I've used it apparently. Play segment. Yeah. Because if I want to say how big the segment is, maybe I'll say segment size instead of memory size. Segment size. Because I know that that number will be at most 16 bits large. Okay, that's fine. And then mem mask is just, so I can give a type to the masks that are going to be working with the memory addresses. But all of those are just the same thing as unsigned integer of 16 bits. Then we have some random stuff, proc ID, process ID for 8 bits signed, and register, which is any register information will be also signed 8 bits. Physical memory is a struct, address space is a struct, segments is a struct, PCB is a struct, MMU is a struct, and then I'm doing this free list stuff. So now that we've gone through all the theory, and we've gone through a rough plan of what I want, let's try do this semi-accurately. So we'll begin with the physical memory, because that shouldn't be too hard. So what did I say? Immediately forgotten. I need an array of size 64. So like memory. Oh yeah, I was thinking of doing chars just to save space, and I'll just fill it with like true and false for like if it's being used or not. So 64 times 1024. Do I have constants already that let me figure that out? Maybe not. Maybe I would make a constant. Hash define physical mem size is equal to 1024 times 64. To give us 64 kibibytes. This is the same as like 2 to the something, right? This whole thing is the same as 2 to the power of 10 plus 6, 16. Ah, so it is this. Did I know that? I did know that. Wait, am I being silly? Yeah, no, that doesn't make sense. Because if the address is 16 bits long, yeah, I'm dumb, sorry. Okay. Alright, so I can get rid of this and put this. Fantastic. Oh, this is wrong. Can I not do this? Huh? Okay. So why was it wrong if I do... Okay, so I must have done something wrong. Oh, I said equal sign. Silly me. Okay, so we have the memory, and we have like... free space total. I want to give this a good name though. Can I use one of these guys? A segment size. It's not really a segment though. Address memory quantity. Memory quantity, is that good? Whoa, I did not mean to do that. Okay, that's my physical memory structure. That took way too long. Anyway, address space. So the address space, I didn't really write that down, but I think I need one. An address space will have a segment for the code, maybe pointer. What's wrong with that? Oh, sorry. Segment for the heap and a segment for the stack. How fun. And then a segment in turn will have a register value for a base register, a bounds register, a grows downwards register towards the bigger addresses, and why did I put a I see, because of that, yeah. Grows down, and protections. I think I'm going to leave protections for now, just because I think I'm probably not going to be doing a whole lot of sharing. I don't think I'm going to be doing that, so I'll leave it. PCB process control block will have a process ID. And then instead of saying the 3 segments again, I can just say address space, can't I? The ADDI. And the MMU, in turn, will need to have just the 6 registers. Now, so it won't be segments. MMU doesn't talk about segments, it just talks about registers. So how do I want to do this? Do I want to make a separate struct for base bound pair? What have I done? Is this lame? Pointer. Okay, so we need a base bound pair for the current code, a base bound pair for the current thingy-majiggy, current heap, base bound pair for the current stack, and maybe something like PIDT current proc. Because again, only one process on the CPU, so there's only one proc using the MMU. Okay, that looks not bad. And then free list node, so it's going to be doubly linked. So I need a free list node previous and next and other things I've already forgotten. The range int starting address. This is what mem address t can be used for. Starting mem finishing. So we'll say exclusive over here, and we'll say inclusive over here. And then here so that's fine. Bing, bing, bong, bong. Yeah, that's fine. Should be fine. All right, so free list. I need a head. Probably a tail would be good. Might not even need a tail, to be honest, but whatever. We have you, we have you. What else do I need? Anything else? Do I want a size? Probably not. That's fine. If head is null, I can assume it's 0. And then yeah, just like do things, I guess. Okay, so hopefully that's the structs done. And then I have all these functions that I want to try. So we'll do the free list stuff first. I think that's going to be the most annoying. Whoops. Okay, so given a free list. Now, I didn't give any parameters to the free list in it because I feel like, you know, I know that when I start, it's going to go from 16 to 64. So that makes me think that hopefully good things will happen, basically. So KIB is 2 to the power of... Hold on. This shouldn't be 1. Am I dumb? This should be, if I'm doing 2 to the power of n, it's the same as 1 shifted n times, right? So if this is 16, then yeah, I'm very silly. Clearly I haven't done enough bit shifting. Okay, so this is the power of 10. So 2 to the power of 10 is, yeah. So then 1 shifted 10 times is, yeah, okay, good. Silly me, silly me. And this should be... Okay. Yeah. Okay, sorry. So this would just give me a way to convert between kibibytes and regular bytes. And then anything else I want? Should be fine. Okay, so I'll just do this really hard-coded for now. And I'll say malloc size of free list. So free list free list node. Maybe I will make a thing. Free list node star free list node create given a free list. And given, I guess, a starting and a finishing, right? Mem address S and a mem address F. I guess I don't need the list, actually. I just want to create the thing. So malloc size of free list node free list node n is equal to that, n starting is equal to s, and finishing is equal to f. And I guess I can set these to null for now and then expect someone else to do it for me. Okay, and then return. A bit chunky, that's alright. So list head is equal to free list node create given the starting, which is 16 times KIB, the finishing, which is 16 times KIB. Is that fair game? I'm a little bit concerned, I'm a bit nervous because, like, should I be casting these? Like, should I be saying like, oh, you should be you? Or something. Like, should I be more careful? Should I be saying that you are an unsigned integer? Like, what if it thinks that it's a signed integer and then something bad happens? Like, because if these default to 32 bits and I try to do bitwise operations with them, then I'm concerned that something bad might happen. I don't know. Anyhow, in this case, list tail is equal to list head. And yeah, this should be null anyway. These should be null at the very start, so that's fine. And then we can return the list. Okay, so that's my function. If I want to insert, given a segment size, sorry, if I'm inserting into the free list, that means it should be a starting and finishing memory address starting. What have I done? Okay. So what am I going to do? I probably want to first create the node. So free list node is equal to free list create given the mem address starting and the mem address finishing. Cool. That's wrong. I need a pointer. Okay, so I have the node. And then this is where inefficiencies are going to happen, but basically I'm going to iterate through from left to right and just find the spot where it should go. The list is always going to be sorted by starting. Ascending order, it's going to be sorted by starting because that's how things are going to go. So, and then I have to be careful what if the thing is empty? So the head is equal to the list head. Or maybe current is better. So the current is equal to the list head. Now if the thing is null, if the head is null, then I should just handle that case straight away. Shouldn't I? It's nice and defensive. Is there a way I can merge them? Merge the two cases, whether it's null or not null? Is there logic that I can do that makes it the same thing twice? Probably, but that's okay. So if current is null, that indicates that there was nothing in the thing to begin with. There was nothing in the thingy-majiggy. There was nothing in the list to begin with. So list head should point to new. List tail should also point to new. And this new can point to null both ways, that's fine. And then return. Since the head is changing value, does that mean anything? I've passed in a copy of the address. That should be fine, that should be fine. We're not creating a new list, we're just creating new nodes, that's fine. Now, if the current is not null, then while current starting, is less than starting, so while current, first of all, and current starting is less than starting, do I need a previous as well? Previous is equal to current, and current is equal to current next. So we move previous along, and we move current along until we find the spot where current starting is smaller than the new segments, the new chunk, the new memory spots starting. So then at that point, the current we're at will either be null, which is fine, or it will be something with a bigger memory thing. Now I think there's some error checking I have to do. If current is not null and current finishing, or rather if previous and previous finishing is bigger than the starting that we've been given, then I think there's a problem. Basically, I'll talk about this since I'll just write out the error message first and then fprintf. Free list seems to try to insert a valid a chunk starting into %d I think I can do this, right? Starting, finishing. Whoa, how did I do that? Oh, finishing, previous starting, previous finishing. Okay, so bing, bong, bing. So basically my concern is like, what if I have like something like this where I have a free list, and let's say for example a node looks like this. I have like 10 to 100, and I have 110 to 140, and I try to insert like 50 to 90 or whatever. This doesn't make sense because like the 50 to 90 is already kind of in here, right? The 50 in particular is already in this section. So inserting this chunk in here doesn't make sense because, and the reason I know that is because, you know, this chunk here ended with 100. So why am I inserting a 50? You know, I should be inserting like 100 to 110 in here between these two guys, right? So that's what I'm trying to get at. If the previous finishing is strictly greater, if it's exactly equal to, that's fine. But if it's strictly greater, then that's a problem. So there's that. Otherwise, hopefully we'll be okay. Previous. So we have previous and current, and we're trying to make previous new current, where current can be null. I have to be careful. So previous is probably, I don't think previous can be null, so previous next should equal to new, and new previous should equal to previous. Didn't mean to do that. And then if current, then current previous should equal to new. But I can calmly say that new next should equal to current. If current is null, that's fine. That's true anyway. Else, if current is not a thing, this is interesting. If current is not real and current is null, then new is the new tail of the list. List tail is equal to new. So that's something to bear in mind. The tail thing wouldn't be that important, except I want to iterate backwards in certain cases. In this case, when placing segments that grow upwards, I want to iterate backwards through the list. So yeah. Okay, a bit of a chunky insertion function, but hopefully I've done that correctly. Let me read through it one more time. I create the new node. That sounds about right. I get the head and I have a null. If current is null, then that means this guy is completely new. We're basically making a new list and we're inserting it in and we're returning nothing apparently. Otherwise, while current is a thing and current starting is less than starting. Yes. Previous is equal to current. We're moving previous to current and we're moving current to current next. That makes sense. Then when we exit, either current starting will be bigger than or equal to starting. Wait. Yes. Shouldn't it be less than finishing? Hold on. So current starting should be... No, I don't think so. Yeah, because it's sorted by starting. Your starting should be smaller than my starting. That's fine, that's fine, that's fine. Eventually, this guy's starting will be greater than or equal to my starting. Wouldn't it be weird if the current starting was I think I can say this. I think that's fair game. If previous and previous finishing, if the previous guy, the guy to my left, has a finishing that's bigger than my starting, that's pretty weird. I'm pretty confident that the previous starting will be smaller because of this check. But the previous finishing could be bigger than my starting, but it shouldn't be. So then that's a problem. Otherwise, I'm pretty happy that the previous is smaller than me, the current guy on my right is bigger than me, or is null, in which case I do all this. Okay, I'm pretty cool. I'm pretty confident this is right. Now we're going to remove so this is me like looking for a segment, right? For now, I'll just iterate one way, but I might have an extra flag just saying grows down, but for now I'll just do it one way. So if not list or not list head, then just, I guess, maybe I'll just do printf actually. I'll just do a warning. Okay, so if not otherwise, list node current is equal to list head. Okay, and then while for, actually, yeah, I can do this as a for loop, couldn't I? Could I? Maybe not. I'll do while loop. While current, while current is not null, and current starting minus current finishing is smaller than what we need, move current along. You know? While it's valid and we move along, we should try to, yeah, look for a segment that's big enough. If not current, warning, I guess, could not find contiguous memory. Trying compacting. That might help. And then you might have to compact the physical memory. No. But I won't do it here. Sorry. Could not find contiguous memory. Request denied or whatever. I won't I didn't put returns in these places. What am I doing? You should say return. There we go. So if current moved to the end of the list, it's null. Otherwise, we're pretty confident that current has broken out of the while loop because its starting and its finishing is bigger than or equal to the segment. So what am I going to do? I'm going to say mem address t. So the starting address is going to be equal to the starting address of current. Now the finishing address is going to be the starting address plus the segment size. So this is the chunk we're going to remove from the thing. If current finishing is equal to this finishing that I found, we're going to remove the entire node from the thing. So free list node previous is equal to current previous. Free list node next is equal to current next. And then previous next is equal to next. If next is a thing, because next could be null, then next previous is equal to previous. And then we have to free something. Else is fine. Else, because we know finishing, because we know this interval, wait, this should be the other way around, finishing minus starting. It finished, yeah, I'm silly. Anyway, because we know that this segment size is bigger than the requested segment size, because we know that if this is not true, if current finishing is not equal to the finishing, that means current finishing is going to be strictly bigger than finishing, in which case this node that we found is more than enough than what we need, so we only take as much as we need and we replace the rest with the node we want. So what am I saying? I need a starting, which will actually, confusingly enough, be the finishing value we found. The mem address finishing will be current finishing, and we're going to make a free list node out of this. New. And we're going to say, I guess I can make these outside. Previous next is equal to new. New previous is equal to previous. New next is equal to next. and then if next, then next previous is equal to new, else list tail is equal to new. And we can free current outside of all this. Hopefully this is correct. And then I should return the segment size that I should return the memory chunk that so not a segment, but rather a memory chunk, which maybe needs to be or maybe, would it be smart to return a free list node? That way maybe I don't have to free anything at all. The current, which has basically been cut out of the free list. The finishing is equal to the finishing, which maybe won't change if it's this case, or maybe will if it's this one. Be shortened down to what it needs, and then we can return current from there. We should say current next is equal to null probably, and current previous is equal to null, so that there's no way it can be reconnected to the list and then return the current. Which means here and here we should say return null, and here we should say free list node. So we're basically returning the information regarding which chunk of memory, physical memory, we're going to be using from this request of like, I want this segment size. I didn't use this at all, but that's all right. Free list clean. What are we saying? I need to remove, so list, if not list, return, list node, current is equal to list head. Oh my goodness. While current free list node next is equal to current next, free current equals next. Yes, and then current will eventually leave and then free the list. Now my question is, was there any other information I needed? So there's a head, there's a tail, which will be freed over and over. Should be fine. Okay, so we clean up the memory, hopefully. That's good. Okay, so we have like this kind of doubly linked list kind of thing. Now, I'm a little bit concerned because now that I think about it, when I return these free list nodes and I don't free them, I'm a little bit nervous about how that memory does get cleaned up eventually, but hopefully it'll be okay. Ensure you are cleaning this memory. Free list clean can no longer access it because the wiring of the free list is now not associated with the current node here, so I can't use it for freeing this returned current. But hopefully we'll be okay. Okay, so we have some functions for that. Okay. So translating a virtual address. So given a virtual memory address, there's a few things we have to do. First things first, I probably have to be given the MMU as well, shouldn't I? That is the major bit of hardware that is going to be responsible for the translation. So so I need to get the mask. So virtual ampersand with the seg mask, and then shift it down So let me just draw this out for myself so I don't make a mistake. So there's 16 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And the masks look like 1, 2, 3, 4. Those are the segment masks. Then 0, 0, 0, etc. So I'm going to get the 4 bits, most significant bits, and then I'm going to shift it 1, 2, 3. Is it 12? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, okay, that makes sense, yeah. Because it's 12. Yeah, I'm dumb. Anyway, 12. So we have to shift down by 12. So instead of saying 12 explicitly, we can say the 16 thing, bit space minus the number of seg bits, like that. And that should tell me, what's this type again? Well, the seg mask is a mem mask type. So if I say mem mask type, hopefully that'll be okay. Segment value so it's, yeah, the virtual, you get the topmost bits and then you push it down and then you get that. So then switching on segval, if it's a bunch of zeros, this is going to be quite hard-coded. I'd rather not if I can help it, but is there a better way I can do this? Probably. Can I make it more dynamic? Like instead of making it really static and hard-coding it in, is there a way that I could make these particular prefixes a bit more flexible, or I could hash define them up top so that a user could, like, maybe that's better. Not, it's marginally better. Hash define code segment bits is 0b0000. Hash define, yeah, anything hard-coded, I'd rather hard-code here, so that's like all in one place. Heap segment bits 0b0001, right? So it's really that 01 we care about, but I need 4 bits. Hash define, maybe I don't actually, maybe I can just say that, but I think I prefer having 4. Stack segment bits 0b 0011, right? So these are the 3 things. So back to my switch case, if it's a code segment bits, then do one thing. Put break statements in so I don't forget. If it's a heap segment bits, then do one thing. And if it's a other one, what was it? If it's the third one, stack, then do the third thing. Okay, so what do I want? I want to say, I want to translate by basically saying the MMU pointer, obviously, the current code base, so the offset mem address t offset is equal to the virtual address minus this base register value, which is a register t, but that's fine because it's the same thing as something. Is register t the same as, ooh, hold on, this can't be 8 bits because register t's hold memory addresses, don't they? They hold sizes and stuff. So it should be the same as, yeah, I was silly. Anyway, that should be fine. These two boil down to make the same type. So, you know, a memory address versus a base, a registered thing should be fine. So yeah, we access the current code base register and we subtract that to get the offset. If the offset is less than 0, or the offset is greater than or equal to the MMU current code bounds register, so this is us making sure that it's within the right limits, then printf See, what's meant when you have an error like this, what's meant to happen is the particular process gets completely disintegrated. But is that what I want? Yes, it is what I want. Error attempted to access address percentage %d. I'm assuming it's not percentage %d because it's 16 bits, but I don't know. For process percentage %d, try to access virtual from the current procedure, and apparently that's illegal. I don't want to exit, but I want to return like I need to somehow remove this process. I have to kill this process. So I need to either return a signal. I have to return an unsigned integer, 16-bit integer. I could make it signed to do -1, but I'd rather not if I can help it because I'll make things really weird. Well, I know that the address 0 will never be used. I know the address 0 will never be used because the address 0 is reserved for the operating system. So maybe I can cheat it like that. Okay. Now I might just say mem address t translation helper, where basically I take this take u, and instead of taking the whole MMU, I just take the base bound pair. Now, if that error checking is fine, if this is less than 0, yeah, if this is fine, then I should be able to do. I need to. This is where I might need the growth thing. Grows downwards. So if it grows down, if that's like the normal one, growing downwards towards big addresses, then we take offset. We add on. Sorry, we take the base, and we add on the offset. Otherwise, I think you're just meant to take the base and subtract the offset instead. Is the big idea. So this second branch is for like the stack. If it grows up instead of down, then you have to take the base, which is the bottommost address, and subtract the offset. Hopefully that's correct. But then again, would that mean this error checking is different? And is the offset different as well? Hang on. If it grows down, then it's this. Otherwise, if it grows up, then it's this, isn't it? If it grows up, then that means this is going to be the bottom address. I have to subtract the virtual address to figure out. Yeah, that's right. Just like that example we talked about. If I'm looking for 15.5, I take this and subtract the 15.5. Yeah. So depending on which way we're going, the way we get the offset will change. Whoops, click the button again. And so yeah, this is now fair both ways. And then we can do another ternary actually. Return grows down, then this. Otherwise, do this. It's interesting because offset is actually this. Wait, have I messed this up? It shouldn't be the base. That's why. It shouldn't be the base. There should be... I'm silly. I'm very silly. These numbers... The virtual minus, like when I'm doing the translation, I need to do my example again. When I'm doing a translation, I do 4,200 or whatever minus the virtual address. I was subtracting the base register, which is a physical address. I'm silly. So I need one more mem address t, the segment address, like starting address. The segment virtual address. Okay. So the offset is grows down. You take the virtual minus the segment v address, yes. Otherwise, you take the segment v address and subtract the virtual. Okay, that should make a bit more sense now. That was very silly of me. A bit chunky, but that's all right. Semicolon. Okay. So here, instead of doing all of this, I can call the function translate helper. Probably give a better name, to be fair. Wait, what? Translation helper, sorry. I need the virtual address, which is given. I need the segment v address. So for now, if it's the code, I know that it starts at address 0. I'll just hard code that for now. BBP is going to be the MMU. The basebound pair is going to be the current code. The current procedure is MMU current proc. And grows down is going to be true in the sense, well, code segment doesn't really grow, to be fair, but we'll say true because that's fine. In terms of the logic for calculating your offset, it's might as well be true. And then breakout. In fact, I think I'm just going to be returning this, won't I? Because it's giving me the address right away. And then I can basically do this 2 more times. Cool. So I know this will be false. That's important. So yeah, for the translation helper, the starting address is always going to, by our code, it's always going to be at 4 kibibytes. Because remember, heap starts at 0, 1. Which means its starting address is going to be 0, 1, 0, 0, 0, 0, which is going to be 4 kibibytes. So 4 times KIB. And then this one will be So the starting address, quote unquote, of the stack segment is 16 KIB. I guess I just want to be careful because I think that's right. Yeah. Because the base register for the stack will point to just below the stack starting address. So like, because I was thinking maybe I should say 16 kilobytes minus 1 because technically the last address being used or the bottommost address being used by the stack is 16 KB minus 1. But I think it's okay if I say 16 KB because as long as I stay consistent with that exclusive logic, like 16 KB over here, 28 KB over here, meaning 28 KB is not being used by the stack, it's right below. I think so long as that's consistent, I think it'll be okay. So I have 0 for the starting, 4 for this one, 16 for this one. I wonder, those numbers are specifically based on these numbers. I wonder if I could sort of reduce how much hard coding I have by forming a strict relationship, but anyway. Anyway, it's fine. We'll leave it like this for now. So now we've managed to translate the addresses, hopefully. And then I have to place a segment. Okay, so this is sort of the generic function, placing a segment of any particular size. So step 1 is I have to figure out a... Okay, so if p memory pointer, obviously, if the free space total is smaller than the segment size, then fprintf, or printf maybe, warning, free space unavailable for segment of size, segment size. I'll return, I won't exit. Okay, how do I determine if I need to compact yet? Maybe I could have a way of determining what the biggest free list node is in my list. It's a bit annoying, but it could work. So one of my types, a memory quantity, largest block or whatever size. So the free list node, when I initialize it, so let me go down to my functions. When I initialize it, wait, did I put it in the wrong place? Yes, I did. You should go here. So when I initialize you, I can say your largest block size will be, hold up, this should say 64. 64 KIB minus 16 KIB. Right? Which is the same as the physical memory size, which makes sense. So yeah, the largest block size is this one. And then the idea is when I insert, can I just be like, if starting minus finishing, no, I keep doing that. If finishing minus starting is greater than the list's largest block size, then list largest block size is equal to finishing minus starting. When I remove, this is trick. Ooh, actually, this might not be so easy to keep track of. Actually, if I remove the largest block size, how would I know what the biggest block size is now? I would either have to just completely iterate through again, which is kind of annoying. Although I already iterate through once, so iterating through again is not that big a deal. Yeah, maybe I'll just do that. I'll just iterate through the whole thing. Update largest block size given a free list. If not list or not list head. So many while loops. While current. If the current finishing minus current starting is greater than current size, then largest is equal to this interval, and at the end of it we will say that list largest block size is equal to the largest. Is this the best way to do things? No, but it's alright, it'll work for now. So we do all this, we do the removal, and then we will just call this function real quick given the list after we've done all the updating and rewiring and everything. That way I just keep this updated. And free list, I don't care. Okay, good. So back to what we were doing, placing a segment. If the total space available is not enough, then we return. If the list, I need the free list. If the list largest block size is smaller than the desired segment size, so we know that there's enough space available, but the largest block size is too small, then we have to do this compacting thing. Probably need the list as well. Huh? Pointer. Ah, of course. Pointer and pointer. So yeah, if the list largest block is too small, then we have to compact the segments, doing this whole thing of this thing. And then after we do that, we can do that thing. We need to look for a segment of a particular size. So I have to look for the free list remove given the list, given a segment size, and grows down. I'll add that, but we're not using it yet. So free list node, the memory that we're going to be using is this one. So this might seem very dumb, but basically all I'm going to do is I'm going to say for int I equals mem starting I less than mem finishing, because remember it's everything from here to here non-inclusive, I think. Yeah, that makes sense. Plus I, so this is my index. If p memory is already equal to true, so yeah, remember, I think I made this chars, right? The actual, wait, not p memory, sorry, p memory data. Yeah, I made this a char thing. So if p memory if you're already true, then we have a problem. Fprintf, this is like an actual error. This is like a logic problem. Trying to insert a segment, but apparently this memory position is already in use. And this is like a genuine, like, oh, we've done something really bad. Otherwise, p memory at I is equal to true. And we do that over and over again. And at the end we say printf placed segment of size from address %d to %d, %d inclusive to %d exclusive. So size, segment size, the memory starting to the memory finishing. Cool. And then we can return. Okay, so what have we done when we did that? We might have compacted the segments. We were definitely removed from the free list to get the memory we wanted. And then we inserted into the physical memory as so. And then, yeah. Okay, so placing an address space, my basic thinking is given an address space, which should be a pointer. What is this? A segment? Okay. So the code segment. So the bound tells you the memory segment size. Your address space, code, it's the code segment we want. We're getting this, we're getting the bounds register specifically. We're going to place a segment, given the P memory, given the segment size, given the list, which I didn't provide, and given grows down, which apparently I can also I'm going to do this 3 times. And then between each time, we're going to set the seg size to be something different. Heap, stack. This seems dumb. I'll be real honest. I'll probably make a helper actually. Yeah, what about instead of putting just the segment size, why don't you put a segment? And then you can be like seg size t is equal to segment bbp bounds, because bounds tells you how big the segment is. That way, this isn't as dumb. Segment, it's the address space code. Free list is list and goes down. Yeah, and in that case, you don't need this here, because grows down can be accessed from segment grows down like that. Good. Which means I don't need this. And then this can be heap, and this can be, that's way better. Yeah, far cleaner than whatever the hell I was trying there. Okay. And then the last internal function before we think about input output is compact segments. So this is the sandwiching thing. So basically, I have to figure out how much memory in total is in the free list, and then basically just make a big block, make one big block that at the bottom, and then I have to do all this copying. Oh, okay. This could actually be a little bit tricky, you know. What do I have to do? I have to go through every segment in the physical memory. Does that mean I have to go through every process? Because like maybe I have to iterate through the process table, find. Ooh, yeah. Okay. Hang on. Because I had a PCB thing, right? Which I didn't write out yet. Maybe I did. I did. So I have the PCB, which gives me access to the segments that I care about. Given all of the PCBs, so PCB table, given all of the PCBs, I go through each of them, I find the segments that are associated with them, which means I can figure out exactly where they're located, and then I can, because I know their base register, I can then move them. Interesting. Okay. So this is gonna be pretty fun. I'll do this and then I'll stop and then I'll keep going maybe tomorrow or the day after or something. So the mem address, next address, is going to be 16 KIV. Right, because the operating system finishes at this address. So this is the next available one. And then basically, I'm going to iterate through all of the processes, which means I need the process table. Wait, why is this wrong? Identifier is undefined, but it's not an identifier. To type. Oh. Process control block. Yeah, I swapped it around. Yeah, and if I'm going to place a segment, this is the only annoying thing. If I'm going to have PCB table as a parameter, proc table as a parameter, then all of a sudden a bunch of things need proc table in the parameter, even though I might not necessarily need it. I only need it if the thing is too small. Okay, I guess I can do it like that. It's a bit annoying, but PCB prop table. Yeah, which means you need it. Yeah, not my favorite way to code, but for now I'll leave it. I want to think about the actual function for this first. Alright. So the next address is this one. And then basically, I can't be bothered having two parameters. And then num. What? We good? Alright. For should be addresses, shouldn't it? Numprox. Ew. Why do I have the same thing? Hang on. Okay. So I get the current procedure. I figure out where your base is. I get your... Ah, of course. I get your code, your heap, and your stack. Okay, the way this is going to work is kind of dumb. Like I said, I don't actually care about growing so much, so maybe I'll get rid of the grows down, grows up stuff. Maybe I won't. I don't know. But... so the code base register thing and the heap base register and the stack base. So I have the three segments that I care about. And basically, what I'm going to do is for each of those segments, I'm going to move them up. I'm going to move them up as high as I can. So the offset being equal to 0, offset being less than the code base BBP bounds, this one increasing, we're going to say the P memory at next address plus offset is equal to true. This is like basically me, wait, what? Oh, sorry. This is me basically doing the copying operation, moving the code segment, moving each bit of data in the code segment, moving it up as high as I can in the physical memory. This is like simulating the copying operation. And we do that for each of them. And then after we're done, the next address is equal to, is increased by the code base BBP bounds thing. We move it along to the next guy, to the next sort of free spot. And then we do this 2 more times. And because I'm copying and pasting, I will probably make a function for this. Yeah, let me do that now. So void compact segments, or yeah, move a segment, given, so it's basically, I want this for loop. So I need the physical memory. I need this one, and I need the code base. Well, I actually just need the bounds, actually. And then I can return the next address plus u. And return this type. This way I'm able to communicate the next. Okay. And then this is going to be, I guess I just need the bounds register, don't I? Okay, so what am I actually doing? Instead of doing the for loop in here, wait, what the heck? Was there a for loop here before and I deleted it? I don't know what I just did. Anyway, move the segment. Physical memory. Mem address, next address, and the bounds. Code base register. Not code base, sorry. Code segment. Okay. I am thinking though, hang on. I feel like I've forgotten something. As I have to actually update the code segments thing. I have to update the base register. So I need to give the whole segment actually. So yeah, this should be this. And then the segment BBP base should equal to that next address because that's where it's located in physical memory. So yeah, I gotta do that. Okay, that's fine. So I do this 3 times. Magic number 3. So the code, I need the code segment. I need the heap segment. I need the stack segment. Now, this is a little bit, the way I'm doing this is dumb because basically I'm squeezing all this memory so tight together that means the heap and the heap and the stack have no space to grow because I'm like shoving them as much as I can. There is no growth space to it, which is why I'm saying I'm going to avoid the growing thing because I feel like it's too annoying. But maybe, what I would do in real life is I would say, after the heap segment, if I've done a heap segment, for example, maybe, you know, add a little bit of extra, like the next address, I should add a little bit more memory so that there's a bit of space for the heap to grow into if necessary. And then the stack, I can do something similar, but that's all right. Yeah, so I do this 3 times. I'm updating, the base register. I'm using the bounds register. Return the next address, and I'm getting the next address each time. And then, yeah, that looks pretty good. So I do that for all of the segments in memory, all of the processes and all of their segments. And then basically I have next address outside the scope. So for size for mem address, this is the same as unsigned integer 16, so this should be fine, right? Basically, my thinking is, I now have to make everything else false. P memory, the memory, empty add equals false. So everything from the next address, like after we've put all the segments in, where am I? After we put all the segments in, blah, 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 next should point like over here, and then we'll go blah, 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 we'll iterate it through all of these spots, and we're going to set these to false. That's what I'm trying to do. The amount of actual free space should be the same. So this should be the same. So this shouldn't have to be updated or anything. I just have to set this to false. And then that should be fine. And the last thing I need to do is update the free list. So what I might do, and this might be kind of dumb, but what I might do is just free the entire list and just make a new one. Purely because I know I need just one node, so I might as well just clean everything. I could try to be a little bit cleverer, only free some of the nodes and keep one node and reassign its values, but I think at that point I'll just stick with one. I wonder if I can, so what I'll do is I'll malloc, where's my init function? I'll cheese this a little bit, hang on. So I'll use this function. List head starting is going to be equal to the next address. So, by default, it's going to be set to 16 KIB, but I'm going to change it. Finishing will be the same. It will be 64. Will be that, so that's fine. Like, basically, it'll be physical memory. So I don't actually have to write this, but I will, because just to make it explicit. And because tail points to the same thing as head at this point, because it's the same node, I don't think I have to update tail at all. I might have to return the list because the list is now pointing somewhere else. So if I don't return list, then I fear that something bad will happen. Now, something I have realized, last thing I'll do before I go to bed, is I think I haven't actually been updating this field correctly, free space total. So anytime I see P memory, I should really make sure that I'm... So moving a segment won't cause that to change, the amount of memory, but placing a segment will cause it to change. So I need to think about that. And I think everything else should be fine. So I think, yeah, placing a segment. I might also have to remove a segment, like remove an address space, but I probably won't for now. If memory space total segment size, that's a problem. If this is the case, then compact the segments. All right, here we go. So I think all I really have to do is be like P memory free space total, subtract off the segment finish. Oh, sorry. The mem finishing minus the mem. Could I just actually hang on? Could I just say the segment BBP bounce? Surely, right? Because I would have used that to figure out the segment size. Oh, yeah, I have segment size. There you go. Okay, so that's it. So that's the whole thing. And then on the flip side, if I remove an address space from the physical memory, if I remove a segment, then I should be increasing the physical memory free space total. But I don't do that yet, so it should be fine. All right. Does this work? No idea. I will not test it properly because I can't be bothered setting up input-output, but I will check if it compiles. Oh. That makes sense. Because I would have, yeah. I should do some forward declarations. Oops. So, that's one function. Move segment, compact segment, free list node create. How do you do compact segment, for example? Never mind. Yeah, that's what you say. I like because I feel like this macros will like trigger into the default to integer types, so I need to do much of it. Okay, hang on. So let me look at all this nonsense. Conflicting type. Wait, oh, wait. My bad. Yeah. If translation, I don't actually call this yet, right? So yeah, but I need to, when I return 0, I need to be careful. Okay, so yeah, I need to make sure I say that. It's fine. I'm going to assume that's because of the same error. Results of comparison of constant 65536 with expression of type mem address t is always true. Oh, whoops. What? An unsigned short, yes. Unsigned 16 bits. Excuse me? Result of a comparison is always true. Did I mess this up? Is this number not correct? Ah, I think it will overflow before it. Okay, I think I understand. Okay, yeah. I think it saved me from overflow. Okay. Hang on. Where is that again? Here? So basically what's happening is because this is 16 bits, this is always okay, yeah. This is I think this number is one more than the biggest number a 16-bit integer unsigned integer can be, I think. Because this is literally 2 to the 16 and this is all the numbers you can make with 16 bits. So this will overflow the 16 bits before um, it actually says this is false. Okay, I didn't think of that. So what I want to do instead, I guess if empty add is equal to ob111 like that. That's what I want to do. Max address and breakout. That way there shouldn't be any overflow because before, like when it gets to here, if I add one more time, it will overflow. But if I see this, and then I'll break out. So hopefully it'll be okay. Hopefully. Implicit conversion from int to mem address t. Oh, really? Couple of things I just realized. When I do this cheating of recalling, where's my compact function? Oh, here it is. I have to say list largest block size is equal to physical memory size minus the next address. Should update that field. Anyway, sorry, so what? So 259 list head finishing. Yes, it's this one. It's 261 now. Implicit conversion from int to mem address t. Ah, because finishing is a mem address, isn't it? And this is one bit. This is one too much. Trying to be very precise has made me quite. Yeah, because this is basically, if you're moving it by 16 bits, that means it takes 17 bits to store all this. But finishing is a mem address, which is 16 bits long. I see. Yes. Okay, interesting. So I have to think about what to do in that situation. If the finishing is meant to be one more than the very last bit, there's two options. Either I say 32 bits, and then I basically say there's 12 bits and there's 20 bits for the segment size and 12 bits for the offset section. 20 bits for the segment section, 12 bits for the offset section. That feels dumb. I want to be able to keep it as unsigned 16 if I can. But what should I do? Ah, the physical limitations of computers has has played me. Oh, I forgot about that. Yeah. So the physical memory is this big. Should I just say -1 or what? Yeah, maybe I have to make it inclusive on both sides. Before I said inclusive exclusive, didn't I? Somewhere over here, I think. I said starting is inclusive, finishing is exclusive, but maybe I should say starting is inclusive, finishing is exclusive, inclusive as well. Okay, I'll have to go through this with a fine-tooth comb to change everything though. Okay, that's fine. That shouldn't be too bad. All right. So continuing on, basically the only real change I've made is this finish in the free list node. Originally, I had it so that each block had a starting and a finishing address, but the starting address was an inclusive address and the finishing address was a exclusive address. Now, I've made it so that they're both inclusive. So like, for example, before, if a node had like addresses 15 KB to 16 KB as a free node, that would mean that this node represented the addresses from 15 KB to 16 KB -1 inclusive. The 16 KB was an exclusive thing. Now the equivalent thing would be 15 KB to 16 KB -1 byte. The reason for that is because of the compilation error I had last time, where like it was saying that I'd have an integer overflow basically. So now, for example, I think the obvious place to look is like in the initialization function. Hang on, what would I call it? Yeah, here. So when I want to create a list and I initialize the list, the finishing address I give is physical mem size -1. The inclusive address -1. So I do that. So remember, physical address, physical mem size is 2 to the 16, right? That's the 64 KB thing. So I subtract 1 to make it inclusive instead of exclusive. And then there was some surrounding changes in places to based on that change in logic. But otherwise, it's pretty much the same. But now the thing compiles. Things compile. But I now need to figure out how to do input-output. So that's what we're going to do now. So what do I need? What have I done? I have a translation function. I have placing segment, placing an address space, moving a segment, compacting. Moving is just like, yeah, for the compacting function. The free list functions. Update largest block size is like super privated. I just use it at the bottom here. Yeah. Okay. Let's see what happens. So my basic plan, I don't really need these print statements anymore. My basic plan of attack is we're going to get the processes, and like last time in the other video, I'm going to say arrival time is fixed at 0 for all the processes, just so I don't have to deal with that. We're going to do like time slice round robin style scheduling like last time. Time slice equals 3 instructions. We're going to store all processes in a PCB table. which I think I made a struct for that, didn't I? Yeah. Each process should have addresses that they access. A list of addresses that they access. What else? So that's fine. And then I need to think about, like, in terms of the simulation function, I'll basically do something along the lines of take the next process, whatever that means, run it for 3 instructions or its remaining instructions, whichever is smaller. Take the next one, run it for 3 instructions or whichever is smaller. For each instruction, check that the memory address is legal. If it is not, kill the process and clean the memory. That's the important thing. I don't know if I did this last time. Can't remember. But yeah, do that. That's fine. And then yeah, that's pretty much it. Okay. So everything that I've written so far is basically the underlying logic functions that are actually going to handle the simulation. But what I'm writing now is like all of the actual sort of front end quote unquote functions that are going to like be the things that the main function interacts with. So how do I do this? So I need to first pass the processes, which I'm going to do as standard input. So I'll do that first. Handle input. I might need my other file to figure out how I did this last time, but it was something like fgets, right? I need the something in the file pointer. I need the buffer. Maybe I will just get the so I had, yeah, so I did this, did a while loop, and then built it up. Okay. This would probably be quite similar, right? But the difference is, I think the extra thing I have to do, because I care about I care about the different segments, I have to think about how big I want to make each segment, right? Like initially. I changed names for I changed structure for this as well. Max access curve. Max access per process. What is the process we need to oh, live from the live field. I'll do that. True. Now live field makes sense. I'll do that. PCB. I might need the access, right? Current access. Sure. Sure. Current access equals 0. Live. I guess that's true, right? Or live, not dead. And then the address space. The address space is something like that. Expression of 5 L. instead of treating them as T, right? Should be that part of whether I and for this, so be careful when I do this. I think I'm saying them as T. Okay, so what we're doing, work the line. Yep, we do all this stuff. String 2K was this current. Oh, it splits the into a string. Okay. Well, just isolate such an alternate string. Oh yeah, you can just call it over and over again. Take the character elements out of there. You convert it, and you get the virtual address out, and then you do that, and then you do that. Okay. Same as you. This looks okay, right? Hopefully we're fine. Number of accesses. We have the finalized addresses, which is being saved into here. And all of this is being saved into the table. But this shouldn't be a... Okay, we'll keep this on the stack, that should be fine. Free list as well. What do I need the free list for? I don't think I use it. Okay, so I have a way of passing the input probably, should be fine. So I can store that input, which is, I can get all the processes that I need. Okay. And then something like, what else do I need? What did I say? Get the processes, arrival time is fixed, round robin style, so I need like a time slice constant. Okay, so simulate. I need to get the input first. So PCB table mask processes. I'm gonna pass input, give it a table. So like that. I don't use table. Hold on. Proc table at the ID equals to this guy. Okay, that's 3 points. Okay, no. Pass table, get a number process. And we say PCB table. Num proc is equal to num proc. The proc tells us the table. Done it. Okay, so the order procs. There are many accesses, etc. And then I need to also get the free list. And the point I need to sign address, which is 16 kb. That's the number 016 is OS. And the free memory finish is memory. Minus 1. There's input to that minus 1. So I copy that correctly. And then num complete procs equals 0. While num complete procs is less than PCB table num procs. So I always have non-complete process to go. So while this doesn't complete process to go, you have to pick the next die. How it is. So we're going to get double. Hold on. I'll say PCB prime proc is equal to PCB table procs at index 0. And we should try to guarantee that at least one process. Okay, so this is actually fine now. Okay, so what does that process go? While time left equals 0 and current proc current access is less than current proc non-accesses. So let's look at index. We expect time left to increase by 1, we expect time to increase by 1. Time is like a round robin. No, round robin. Current proc non-access increase by 1. This is the expect. And then outside if current proc current access equals current proc non-access, so finish the number of pages accesses, then the non-complete proc increase by 1. The current proc alive should be set to false, it's done, and we should pick next. Given the current proc and given the PCB table. Address of the PCB table. Okay. What if I say current proc? This indicate that it's prematurely to access. Or if I have 4 accesses, then by the way, we just exclude the guy. Negative. Round time is 0. So while these are true, we have to. So mem st is equal to current proc. Access that means current proc. Current access plus. So make sure we current as well. Well, actually, sorry, translate virtual address. Given virtual, given low. It's not heads. Photos. How does it work? So the enemy has to keep track of process ID, but also a baseline pairs. Good Apple stuff in Apple. And then use stuff and use current code. Size of baseline pair. And the baseline pair. Might as well be this. base is equal to base, BP pounds is equal to pounds and reg t base and reg t pounds. Fair? Or no? No, 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 fair. Okay. BP so I need code base, code pounds. I need key base pounds. Oh, yeah, right. Stack base and stack pounds. I want the code base and code pounds. And then no, what is it? Yeah, current of Is this dumb to do it like this? Like, wouldn't it be smarter to have like an MMU but no real register values yet? Like maybe I just zero everything out? Is that better? Because like the MMU in itself, when you create an MMU, it shouldn't have stuff in it, like information about the processes yet. Maybe it's better just to do this and set the values appropriately after the fact. You know? This is my decision. So everything's zeroed out. So in my simulate function, we have yes. Okay. Star. Okay, the other thing I have to do before I do any simulation stuff is I have to actually figure out how the address spaces are going to work. Like, how are we going to place address spaces and stuff? Will I make all the address spaces look the same? I guess so. Oops. So I have segments. Okay. So go down and then we zero out. Then like set up using like I think it's a tab control the actual values. Like base master side. Just let me calculate. But the address space is chosen by the actual OS site, so we got runtime. Well, so okay, HT, code base, HT, code times. Yeah. Breakdown is true because base is code base and bounds is bounds. Okay, fine. See, but I have a function that places the address space. So maybe that sets the values for me. Yeah, okay. Here I forgot. Here is where I let the operating system, quote unquote, figure out the next place to put the segment. Place a segment of size here. So given the free list, and given a particular address space, yeah, but I know at least the bounds has been set already. The segment's bound thing has already been set. What about the base? When I place a segment, shouldn't its base be set? Yeah, it should. Which means I didn't do this correctly. setting the base of the segment. Yeah. So I think the bounds shouldn't be set to any, the actual base shouldn't be set to anything. Only the bounds should be set when I do the address space thing. So it's good. Yeah, that's good. Cool. So yeah, I know that bounds. I'll never it's gonna be the first alphabet. Okay, thank you. Hmm. So I wonder if it's a good idea to just give the address space away. Just to give it away. The bound space. I need to be defined how big I want to change the code segment and the code initial key segment initial size. I think that's a good idea. Code size. Size. So like this is my so like if it's address space 16 KB, I might expect 2 KB. And then might like we'll say 3 KB and we'll say 2 KB. This is the thing. So the code bounds the size of the segment. Size. So the address space has been initialized, but it hasn't actually been placed yet in the memory. That's why we have to set the bounds because we know how big we want to make it, but we don't know where it's placed, so we can't set the base value yet. Okay. I feel like I need to know when to place an object. Maybe I need a boolean like placed in the PCB. Originally false. Do I not have P memory yet? Physical memory. Free space total. So the memory is equal to array. My round is of size 64. Free space total is equal to size minus the size of OS. 16. How do I get to minus the size? Yeah, sure. Okay. I'll say 4 less than current size. I'll say the RAM will be memory, and that's true, that's right now. And then for the half afterwards, so I remember that I had it wrong previously. When I oh no, right. Like I said, I should say the next address contributed OS. Yeah, I'm pushing this outside the address. Yeah, the address. Just place. Okay. Place memory. It should be possible. The address space is free list. Free list? No, not list. I got yeah, place. I've interior placed memory. Okay. I just place. Everything nice. Place. It's false. And we should place the address. Okay. Let's do this. If the address is 0 times 0. Process. Process. And you can out. You should say kill the process or line false. That's not current time. Maybe I would say whatever. So yeah. Okay, so. Okay, so. If this process is 0, how does it go? Then there's another left time. It's really neat to example speech. For processes address system. I think the actual address is right for the process. Okay, so function access manually, and then otherwise. Something like this. Okay, fine. should reset the time slice. Hold on, I did this wrong. These two things indicate that this should happen. I wonder if it should be like this, and then if so these two things, if this is true, this tells us that the procedure actually completed, like completely done, in which case number proc should increase by 1, current proc alive should become false. Now, if these two things are true, or RR time is equal to 0, then we have to pick the next guy. Yeah, these are two separate things. Do this as well. If not, if this was null, then we should be done, I think. And if it's not placed, then we should place the address and we should set this to true. Did I do that at the start? Yeah, okay. Okay. I mean, I think I did it. This could have been the main function, to be fair, but it's alright. Simulate should be broken up into other parts as well, actually initializing all the structures and stuff. I guess I did do that to some extent, but I guess you could be unsigned as well. PCB. I wonder how much this. I wonder how close I am to compiling. Oh. Oh, I need string. Oh no. Wait, what? I need a string and access string. Seems right. And I need the finalized address, which is narrated. Alright. This is local instance. Oh. Right, because it's not going to be weird. I think I put in the child expression. Sorry, what? I think I put in the child expression. No, I was saying what? It's memory. It's maybe it's easier. Same thing. Oh, yeah. An array of pointers. Double star. This is basically double star treatment. I think. Not also ooh. Sorry, yeah. Conversion from int to unsigned. Change the value from that to that. Yes. So this memory. If this memory size is 1 or R2 to the power of 16 minus the kernel block size is 16 times KD. How is it right? Is what I want. Well, let me ask it. Oh, there, okay. The other function I was thinking of was something like. Okay, there's other functions I need. I need something to remove address spaces. I need a function. I can't. One of the other criteria for picking a pick next is like, what if there's not enough memory to put, like, if it's a if it's a process that hasn't been placed yet in memory and there's not enough space, then it shouldn't be the one that's picked, you know? Maybe I need to be like int. Is this bad? Oh, fair. Okay. Free space is unavailable. So if this happened, I'm going to return a 1 to indicate there was some kind of there was a error with doing this. And then if there's no problems, I'll return a 0. And that way, it should have bought straight away actually. So if 0, if 0. Okay. We're pretty confident this will work. We're less confident of this one. So while this is giving 0, oh, this is really badly written. Hang on, let me do this again. So what am I trying to do? We pick the next guy. If the if okay, so while it's not placed, the current process, while the current process is not placed, try to place it, but if it doesn't give a 0 result, then we have to go to the next guy. And hopefully we'll eventually find someone that is able to actually place the result, place the address space. And I need to remove the address space as well. You know, I have placement. I need to remove something as well. Base sign. Is it decided? inclusive, I think. Memory, free space total, memory, I don't know, and I could do it again. And then also back to free list, right? Like, I have to be like free list insert, given the list, given the starting and given the finishing, inclusive starting and finishing. When I insert, I was supposed to merge blocks together if they were contiguous, but I'm not sure if I've done that properly. Actually, I definitely haven't. I have this. During one, I find the place where current is signed past and previous before is new over here. If not current, with the end list, order knows the end, then I have to. Well, that means I continuously found. I kept finding node that had signed up to small, which means my new node should go to the end. Okay. So that's like if current is a thing. If previous is legit, that means it was 90 and no dates. We move along somewhat. Current has been held a bit previous finishing is equal to. While previous finishing. If previous finishing is equal to that's one, because it should be the same. If previous finishing is one less than sign, then previous is equal to the finishing. If, just say if current exists and current sign is smaller than this finishing I'm about to put, or equal to, it should be the same. Weird stuff. Right, so here's the current and current starting is equal to if previous finishing plus 1 is equal to okay, so I don't know something like that. What I do is recognize whether I have to merge all together or just do them together. But this new node has a bridge, so I'm using the bridge between previous and current. So actually, if I merge all together, there's one node, or okay, if previous and current, just very we'll try to be more clever. If previous finishing is equal to starting minus 1 and finishing itself is current starting minus 1. So if the previous and the new and the current form one contiguous block, then we merge all together, creating a new node. Then I can say maybe previous finishing is current finishing, right, and free the current. Maybe like free is node next is equal to next. Previous next equal next. If next then next. Previous. Choose previous. And if there is next not, then this tail should be previous. And that's current. So this is merging all the information from the previous node, the new node, and the current node into one massive free block that now set into previous. Else if previous finishing is equal to starting minus 1. So then previous finishing is equal to finishing. Everything else is the same. Because that starting is bigger than finishing. The current starting is bigger than finishing, so all the like conditions of the previous hold. That's this, yeah, else if previous no, else if finishing is equal to current starting minus 1. If the new finishing is right for the current starting, then I can say current starting is equal to starting minus new node. Else if I want to do any kind of merge, then I just insert new node. If current and current previous new node, this tail is new. Else if there's a previous with no, else if there's a previous with no current, then it's merging happen again. Else we create a new node. Else there's no previous and no current. Okay. If the current will mute according to the individual on the wall. Then the current which box size? I'll put So another one. If previous state null is at the head of the list immediately too much. Basically, actually. Do one generate non-function with remove segment. So instead of free segment and we I need that yeah. Remove segment given physical memory segment which means space code. Well, so now I have to like remove from the function. Remove addresses given memory given data space general box. And freeze. That way we can regain some space back. Well, by then change let's see what happens. So if I say that needs to be like just numbers. So let's say I have a 16. These are the addresses I'm allowed to use. This is as big as I can get. Any number between 0 to this, I'm allowed to use apparently. So let's say I go like, so these are all code segment addresses, and then I have like so like remember if it's 0, if in binary it starts with 0 0, if it's 0 0 0 0 in binary, when you write it with 16 bits, then it's a code segment. If it's 0 0 0 1, then it's heap. And if it's 0 0 1 1 and then some stuff, then it's stack. So let me think about what numbers I'm actually allowed to do. So 0 0 0 0 followed by 12 bits. 0 1 2 up to 11, right? 12 13 14 15, yeah. So what's the biggest number I can make? It would be 2 to the 12 minus 1. So any address between 0 to 4095, this is code segment. This is code segment addresses. Now, if I had a 1 here, then so 4096 up to, what's the biggest address I could make? A bunch of 1s here, so it would be 2 to the 13 minus 1. Because 2 to the 13 is a 1 over here and a bunch of zeros. So subtract that. Yeah, subtract 1 from that. So 8191. These are the heap things. And then if you have 2 1s over here, what's the smallest address I can make? It would be a bunch of zeros over here, and then 2 1s here and here. So 2 to the 13 plus 2 to the 12. 12288. That's the smallest address I can use for the stack. And the biggest address is all 1s, which is the 16. Two to this 14, whatever. 11, 12, 13, 14. 2 to the 14 minus 1. 16383, which is the 16 kilobytes thing. 16. Right, 16 times 1024 should be one more than that, yeah. So these are the sort of addresses you would expect to use for code, heap, and stack. So the question then becomes, considering the fact that I limited the sizes of each segment, didn't I? Wait, is this the right? It's the wrong chapter. I said that the code segment should be at most 2. Should I just make it 444 so that I can use all the addresses I want? It's a bit cheap though. I was trying to make it so that they weren't the same size all the time. Didn't quite need to do that. Code segment. Okay, I'll just stick to the first half, and then I'll stick to the first 3/4 of this interval, and I'll stick to the second half of this interval. We'll see how that goes. Okay, so I do some code retrievals, and then I do some heap stuff. So like 4097, 4098, 4099, and then I do like 16382, 16381, 16380. I'll just do that for all of them. I'll do 2 things like that, and let's see what happens. So if I do clang, oops, not that. What am I doing? Does it wait for input? Okay, good. So then, if I redirect, yeah, fair enough. My bad. Place the address space. Place a segment. Free list remove. Oh, how interesting. Previous next equals new. Address points to a 0 page, so I'm accessing a null thing. Oops. I think I do need to rewrite my my free list functions because I think I did them really badly. Yeah, you didn't actually check if it was null or not. It can very well be null. While current finishing. So I'm looking for the place where what am I trying to do? I'm looking for a node that has the right segment size. Okay, so while you are too small, do all this. So you're moving along until you find a block that is the right size. Current should point to the right size. Starting. What is finishing? Oh. So this might be null, yeah. If previous, then previous next is new. Else, I think the head of the list is equal to new. I think that's the grand scheme. Oops. Ah. 16384. How intriguing. 16384. Is that like one more than... Yeah, okay. The reason I think this makes sense because the OS goes from 0 up to 16383. So then it would make sense for the first segment. It would make sense for my code to put the first code segment of the first process from here up to 16384 plus the code segment is 2 kilobytes big and then -1. Yeah. Okay, so that makes sense for that number. So that worked. And this is probably a off by 1 error. Trying to insert a segment, which would be the heap segment, trying to insert it, but this memory 18431 is already in use, which indicates that I probably messed up because of the free list or something. So when it's time to yeah. Yeah, it shouldn't be 18431. It should be 18432. Should I say if previous? Yeah, like this one. Since finishing, what is finishing? Finishing is the finishing thing that's being removed. So should this be finishing +1? Because like this guy, this finishing is being used. Starting's being used, finishing's being used. So the next free list node should be finishing +1. Yeah. This is a result of the change from exclusive to inclusive. Let me try this. Oh crap. Come on. Attempted to access address 5. That failed? What's wrong with that? Ah. Where's my... Okay. What? To compile. Bounds 0? That's not good. Ah. That's not good. I only had 2 processes, right? So what happened there? Why am I placing a segment and a segment and a segment and then placing more segments? What the heck happened? Why would that happen? Did I forget to mark it as placed? Ooh, I only said it once, that's bad. If I try this... Okay. Let me just check what happens now. Okay, it terminated though, which is good. One, two, three. 1, 2, 3. Illegal access. Address 5, the physical address was 0. Oh yeah, that's gonna be a problem. It's gonna return 0 for the physical address. There's no point in doing that. I forgot. Alright, final push. I'll see if I can fix this and then I'll go to bed. Okay, this is weird though. Attempted to access address 5 for process 0. Offset. Attempted to access this guy. The bounds is 0. The bounds is 0, which indicates that when I place... Bound shouldn't be 0 actually, now that I think about it. I set the bound immediately. Didn't I? Like when I do segment init over here, when I first create a proc, like I do all this nonsense. This is, 1024. Let me just check something. Oh my god. Keep Look at that. Yeah, that looks right. Why is the bound 0 if the bounds are not 0? What is this? I must be accessing this wrong. Okay, when I pass this BBP, how did I do that? Because apparently I've done this completely wrong. Oh, I was trying to be smart and use an MMU, but I forgot to actually set the registers of the MMU. Okay, I see. So when it's time to pick the next guy, okay, yeah, because I mean, yeah, true. My current proc is this, which means MMU, current code, okay, hang on. Set MMU, given an MMU, and given, okay, let's see if I can do this. Bang, and then MMU. This basebound pair is the same thing as your basebound pair, right? And then your heap and this is it. This is basically it, right? Where's my init MMU function? Here. We'll say MMU set. This is my function. So every time I choose a new guy, so when I choose a new guy, I have to do things like this. Oh wait, maybe I should place the address space first, and then do this. And then I'm so confused. I don't really want to do this until I'm sure that okay, I think here is a safe place to do it. I think by this point I've like figured out exactly what my current proc should be. And then it should be good. Alright, let's try this one more time. Oh crap. Ah, I'm dumb. Hang on. This was the segment. I have to say BBP or whatever. Isn't this like a code smell? What's it called? The one where you have like get after get? Come on, this is gonna work. Ooh, okay. The last thing I want to do is see if I can figure out exactly what segment it's located to at. print what segment it is. Hold on. It didn't even switch the thing. Oh, I know why. It should be +1 here. I remember now. Yep. Current proc is 0. Current proc is 1. Then current proc is 0 for 3. And then current proc is 1 for 3. And does all these accesses. Does all these accesses. Access after access. And then eventually, I guess we're done. 16. Yep. Wow. It may have worked, kind of. What? And then let me see, what happens if I try something in between? So like 8193 or something. Should have been violated straight away. So 0, 1, 2, 3, 4, 5, and then it should have been like bang. Segment bits are mangled. Good, yeah, pretty much, because it's pointing to that spot where it's like 0, 0, 1, 0. It'll be those segment bits if it's between here and here. Because this is 0, 0, this is 0, 1, and this is 1, 1. Anything between this region and this region is the 1, 0 region. So good, yeah, good. Try to access here. Nice. Nice. Okay. Okay, cool. I really want to print the segment that it's associated with, which means instead of I might need one more struct. Struct segment address pair. So mem address t address, and then what's wrong with that? Semicolon or something. Yeah. I give the address, and I also give, this is 8 bits, right? Or 16 bits. And then I also give the, should I do it as an enum? Maybe just char is fine. Char segment type. An enum is better, but I'm lazy. Fantastic. Okay. So when I want to translate an address, I will return this. Or maybe I will just pass in this as a pointer. This is the code segment, and we'll return the address. I hard coded these, that's annoying. I forgot I did that. Heap. Segment type equals stack. So we give the address and then we'll just return the address as well. That way the signature doesn't change too much. And basically, all I'll do is I'll pass this guy in. The segment is equal to this guy. Virtual and then sap segment type. And hopefully, I don't know if I've done that correctly, but it's fine. Ooh, I'm not sure about that one. 1, 2, 3, 4, 5, 6. 1, 2, 3. So the first. Okay, let me get rid of view real quick. So you should all be C, good. And then you should all be C, yep. And then you should be C, and you should be C, and then it should go into the heap, I think. Ooh. Wait, was it doing that before? Did I break something? The offset is 12,000. Oh crap. The bounds is 2048, which sounds correct. Attempted to act. Was this happening before I didn't realize, or what? Attempted to access address 4097 for process 0. The offset is that guy. Offset is well, assuming it's this guy 4097. The offset should be 1. So right before the offset, put the segment v address. The segment v address is 16384. I don't know where that came from. Four zero 4096. Yeah, what? Hang on. U and then U. That's process 0 doing the first 3. This is process 1 doing the first 3. Process 0 doing the next 3. Process 1 doing the next 3. That should be all the code fetches. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. And then we get to time 9. Oh, sorry. We get to over here. 4097, so it's definitely that guy. Segment v address is this one. Ah, right. Okay, so it thinks I'm in here when I don't think I should be in here. I should be in here. Oh, this is so annoying. Wait, hang on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, it's 0, 1. Why is it what? Oh my god. Okay. Bit space is 16. This is 12. Or 4, sorry. To make 12 overall. I shifted down by 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, the 1 is there. Yeah, what? Oh, it's poor. I forgot break statements. There we go, that's better. Yeah, now we got the heap. Good. And then some stack. Okay. The map looks pretty good. The only issue is it's hard to know exactly where things have been placed. So like this is the code segment. This is the heap segment, and this is the stack segment. Code, stack, heap. That's exciting. Alright, we'll go to bed. It should be good.